All right, hey, what's up, everyone? Just kind of want to give you all an idea of what's going to happen over the next month. The end of September and the beginning of October, not ideal for the way that I had hoped for this semester to go, but it is what it is. I'm going to make a couple of lectures for y'all to view over the next week and just kind of give you a little bit of revisiting the nitrogen cycle. Kind of refresh your brains. I know for some of you it's been at least 2 semesters. Some of you it was last spring. We're going to have fall break October 12th, so there's no class there. I will be back on the 14th in class. There will also be a quiz available going over the lectures that are made here. And then on the 19th, which is like 2 weeks from Tuesday, you need to turn in the first rough draft of everything up through materials and methods. This is important because this is going to give me an opportunity to provide some feedback to you so that your paper can improve. This is probably something you have not done, and I recognize that, but I need you to turn something in to me so that I can start reading and I can start providing feedback that is going to improve your paper. Don't turn this rough draft in. It's worth 15 points. And also, if you don't turn this rough draft in and you just decide you want to turn the whole paper in at the end of the semester, it is likely to come back with a lot of red marks and a lot of points deducted, and that's not a good thing. So I would strongly encourage you to work in your groups and try and get some introduction and some literature review. And your materials and methods you've pretty much kind of written up or at least done, so that shouldn't be too difficult. Week after that, almost the final week of October, assignment 2 is going to be due, and also quiz 4 will be due on the 28th. And we will still try and shoot for exam 2 on November 2nd. All right, so moving into the nitrogen cycle, one of the most dynamic and intricate cycles, nutrient cycles that you will encounter. It's constantly changing, and it's constantly changing back to something it just changed from or changed to something new, and it's very difficult to predict which way those equations are going to happen. Don't get freaked out by this. We're going to go through this step by step, and by the time the exam comes, you will be experts in explaining the nitrogen cycle. I also did post this in iLearn, a blank copy for you to practice filling in. You will need to be able to fill it in, but you will also need to be able to explain each of the different transformations that happen throughout this process. So nitrogen is actually 79% of the Earth's atmosphere. It is as an N2 gas, and it is part of the central molecule of chlorophyll. And so when we apply nitrogen, we see the green up because of the increase in chlorophyll production. Plants reflect the green light. They absorb everything but the green light and reflect that. And it's because of the increased nitrogen that we see the results of our fertilizer. So there are 2 plant available forms. We have ammonium, which is NH4+, and we have nitrate, which is NO3 negative. These 2 plant available forms have an influence on our soil pH. So we will have this root exchange with hydrogen. If you remember from the direct method, our roots exchanged a hydrogen into the soil and actually exchanged a potassium off of that soil colloid. That potassium then moved in through those protein membranes and into the plant because of the electrochemical gradient. Well, ammonium and potassium have the same positive charge. therefore that same process, and that is how ammonium makes it into the plant. And then also nitrate, there's an exchange with a carbonate or a hydroxyl, causing this increase in the soil pH. But you'll hear me talk about later some of the changes that happen might be opposite of this. It just depends on the transformation. So ammonium is typically, when it is taken up into the plant, is going to lower the pH. Nitrate, when it is taken up into the plant, is likely to increase the pH. So our sources, atmospheric N, obviously just mentioned that. It's going to be a part of organic matter. But primarily, we are going to add some synthetic fertilizer to the soil. We cannot get ammonium nitrate anymore. This used to be the go-to fertilizer source. As we've been doing our fertilizer calculations, you've seen me use ammonium sulfate. Urea is our most common source of fertilizer. It has the highest N content of any of our granular fertilizers. Some students have used urea ammonium sulfate, and so what they do is they actually mix, let's say 50 pounds of ammonium sulfate, 50 pounds of urea. 46 and 21 is 37. 67, and half of 67 is 33.5. And because we have half of the sulfate or sulfur content in that 100-pound bag or mixture, that is why we have a percentage of 12% sulfur. Liquid UAN is also used for more banded applications. We tend to use these in corn and cotton. We were able to band that application right next to the roots, so that is the right place. And it's easier to handle. It just might require some special machinery. And then out in the Midwest, like when I think of Midwest, I'm thinking Oklahoma, Kansas, Nebraska. They apply an anhydrous ammonia following their crop. They will harvest the crop. They will come back and apply this anhydrous ammonia, typically in like November. Because the soil temperatures get so cold, it remains as a gas and is stable. And then once the springtime and the soil temperatures start to warm up, they don't have to go back out and apply that. They're able to allow the temperature to drive those transformations. So some of y'all might remember me asking this several times from soils class about the fate of nitrogen. What is the overall fate of nitrogen in the soil? So the first thing, this might not necessarily be in the soil because we're fixing atmospheric nitrogen. So the first fate is going to be fixation. And this fixation is occurring typically in our legumes, alfalfa, soybean, peanuts, our legume type crops, vetches, some of our cover crops take advantage of this nitrogen fixation. It can undergo mineralization, which is the conversion of organic nitrogen to inorganic nitrogen. Next, once it becomes ammonium, within mineralization, there's aminization and ammonification. We'll go over those in just a moment. Once it becomes ammonium, it can undergo nitrification. And so nitrification being the conversion of ammonium to nitrate. It can be taken up by the plant, which is the most ideal scenario. That is the purpose for applying our fertilizer. And we would like for our plants to take that up as much as possible so we can minimize our loss to the environment. So fixation, mineralization, nitrification, plant uptake. Next, it can be immobilized. So if our carbon to nitrogen ratio gets greater than 25 to 1, the microbes will then take that available nitrogen from an inorganic form, such as ammonium or nitrate, and convert that back to an organic form so that they can decompose the carbonaceous material in the soil. And then into our losses, we have nitrate leaching, because nitrate is an anion. It is not held tightly to the soil colloids. It is also very water soluble and therefore is easily detached and can be leached through the soil profile given enough water. 2-to-1 clay fixation, if you recall me talking about those 2-to-1 clays being able to shrink and swell. So we have enough water that comes in there that makes those clay layers swell. The ammonium is then able to move more freely through in between those two clay layers, but as that water is then used by the plant or is evaporated out of the soil, those clay layers will then shrink back down and they will lock that ammonium in the voids made by the tetrahedral layer. We have ammonia volatilization. This is the volatilization from ammonium, NH4+, to an NH3 gas, which is then volatilized into the atmosphere. About 30% of our fertilizer can be lost from this process. Next, we have denitrification, which is the conversion of nitrate back to into gas. So that completes the nitrogen cycle. So starting in the atmosphere, it can be fixed by the microbes. It can undergo mineralization, nitrification, plant uptake. It can be immobilized, lost through the soil profile, can be fixed, volatilized, or denitrification, which actually begins the fixation process all over again. We're going to go through these a little more in depth, one by one, where they fit in that actual diagram. And by the end of this month, you will be nitrogen experts. So here we have our atmospheric nitrogen, which is being fixed by our legumes, the rhizobium or the bradyrhizobium, the bacteria that infect or inoculate those legume seed, form nodules. They have this symbiotic relationship with that plant where they provide nitrogen. The nitrogen is carried up the xylem into the leaves where it performs photosynthesis, forming C6H12O6, glucose. That glucose is then transported back to the roots via the phloem, and those nodules actually get some energy from that. This is also talking about our soil organic matter. So this is the organic nitrogen fraction of the soil that will then undergo mineralization and be converted into ammonium. So, second most important biochemical reaction behind photosynthesis. It is carried out by a cluster of bacteria or actinomycetes and cyanobacteria. And interesting to note, there's about 140 million tons of fertilizer being produced a year. However, almost 280 million tons of nitrogen is being fixed per year by these rhizobium and bradyrhizobium. So, kind of difficult to grasp, put my head around that these little small nodules are actually fixing more nitrogen than we are actually manufacturing. Again, a couple of the most common bacteria that form that symbiotic relation where into gas is converted into this organic this organic nitrogen or this amine group at the end of this. It's about as much organic chemistry as we get into. So we have this nitrogenase enzyme that actually catalyzes that conversion to ammonia, which is a gas. And then when we have those organic acids or amino acids and form proteins, which are the building blocks of our plants, that nitrogen can be used by the host plant. It is leaked out of the roots and might be available to surrounding plants, and other heterotrophic organisms can immobilize that nitrogen, which then becomes part of the soil organic matter, which will then undergo mineralization and then be provided back to the plant. So we had atmospheric N2 fixed. Remember, this was our organic fraction. Now we have moved into mineralization, where we were converting organic nitrogen to inorganic form that can be then taken up by the plant. There are two processes for that. That first is that aminization, which is that conversion of N2 molecules into some amine group, some amino acid or protein. That is reduced even further into ammonium through the process of ammonification. So mineralization is a two-step process. First, it is aminization. Followed by ammonification. So here we have the conversion of organic nitrogen to ammonium through aminization. We have amino acids or amines. That's what this is. This NH2 is an amine group. Some of you might remember that from chemistry. But notice that we have urea here, which is one of our synthetic forms. Like this can also be a molecule that is formed on its own. However, we use urea because we can actually pack that. We can actually condense the amount of nitrogen in urea that can be converted from urea into ammonium. And I'll go over this process on the board when I get back. Next, we have ammonification, where the products of aminization are converted to ammonium. So here we have our amine group. We have water that converts to ammonia. There will be this functional group of organic matter and energy. Once converted to ammonia, we need to this chemical reaction will actually require a hydrogen from the soil to form ammonium. If we take a hydrogen out of the soil, if we decrease the hydrogen content of the soil, what happens to the pH? Does it increase or decrease? If we remove the hydrogen from the soil solution, does the pH increase or decrease? The pH would actually increase. It would become more alkaline. You might recall me stating that when I was explaining that little table on how we classify the acidity of our soil. I like to use the term more acidic or become more alkaline. In this case, the soil would become more alkaline because we are removing a hydrogen content. We are removing a hydrogen ion, and we are actually technically increasing the hydroxyl concentration. So once the nitrogen has been mineralized into ammonium, once it's undergone aminization and ammonification, it can be taken up by the plant. It can be volatilized. For me, this volatilization process, given the right soil conditions, is likely to happen before the nitrification process. But it just doesn't matter. Like There are several fates of this nitrogen. Once it has become NH4+, it can be immobilized by microbes or fixed in those 2-to-1 clay layers. The way the chart has this, or the diagram has this drawn out, is going to be, it will then undergo nitrification, which is the conversion from ammonium to nitrate. And I'll explain this process in just a moment. So here we have our ammonium ions, our ammonium cations, in the presence of oxygen and this nitrous ammona species, this ammonia oxidizing bacteria. So I think of oxygen, ammonia oxidizing. Look at all these O's in here. So this is actually an oxidation process because there's oxygen. I know, shocker, right? We kind of keep it simple. So we have this oxidation process that is occurring. It's being sped up by this nitrous ammona species, where this ammonium is then being converted into nitrite with an I, Nitrite. NO2 negative is actually very toxic to the plants. So we would hope that this process or this chemical reaction is quickly converted into the next one, which is going to be the conversion from nitrite to nitrate. There's something I want you to notice though. What does these 4 hydrogens that are actually created or that are dissociated from this ammonium, what happens to the soil pH when those hydrogens get released back? So the hydrogen concentration increases, the pH becomes more acidic. So we just had, just previously during this process, we just had this ammonification where we removed 1 hydrogen from the soil and it became more alkaline for a brief moment. It underwent this nitrification, and we have enough of that, and we are now changing the pH of our soil again, and it is actually becoming more acidic through this process. So during the first oxidation of ammonium, we are changing the pH. It is becoming more acidic. Next, we have nitrite. Nitrite in the presence of oxygen and this Nitrobacter species, which is a nitrite oxidizing bacteria, then forms nitrate. Once nitrate is formed, it can be taken up by the plant or immobilized by the microbes should our carbon to nitrogen ratio become greater than 25:1. However, because it is an anion and it's also very water soluble, it can be quickly leached or run off. It can be lost, either quickly leached through the soil profile through nitrate leaching, or it is susceptible to runoff. Once it runs off, we can have eutrophication of our streams, lakes, rivers, ponds, but most significantly is going to be this eutrophication of the Gulf of Mexico and the hypoxia zone. We can also have groundwater contamination. So the EPA set this maximum contaminant level of 10 parts per million because kind of back in the 70s and the early 80s, they had nitrate contamination in their water, and the moms and the pregnant mothers were drinking the water that had the nitrates, and when the babies were born, the nitrite was actually looking for an oxygen in order to form nitrate, and when you take that oxygen out of the baby's bloodstream, it was actually causing them to kind of suffocate, and they didn't understand why. Come to find out, they tested the water, found out that the nitrates were excessively high, and they decided to put it into that, and set that maximum contaminant level at 10 parts per million. So here we had our N2 fixed. We had, this was actually our organic matter. We underwent mineralization, ammonification, ammonization, ammonification, nitrification. Either ammonium or nitrate can be taken up by the plant. It can be immobilized or gone through nitrate leaching. Again, this diagram is set up a little different than what I would as soon as I introduce mineralization. I like to talk about immobilization because those two happen back and forth. They're the reverse chemical reaction of each other. Some of the factors that are going to affect that nitrate leaching is going to be rate, time, and source of fertilizer. So this is where our 4R nutrient stewardship comes into play. What the cropping intensity is, how much fertilizer is actually being applied, and then also how much nitrogen is being taken up. And we would hope to have a greater in-use efficiency so that our nitrogen is not being lost to the environment. Our soil profile characteristics, so what is the structure? Do we have a lot of clay? What is the CEC? What is the pH? Temperature is going to play a role in this. How much water is there? How much oxygen is there? Water holding capacity. Organic matter content. Also the quantity and the pattern and the timing of irrigation or rainfall. Not that we typically have a problem with irrigation in this part of the country, but rainfall is certainly one. We do not lack rainfall, and as typically like 50, 60, maybe even 70 inches of rainfall a year. Next, we have the mobilization, which is a conversion from inorganic to organic as a result of the microbial requirement. And so there is a carbon to nitrogen ratio that kind of dictates what this is. Typically, you will find this ideal kind of value for microbial populations at 24:1. It will change depending on which book you read, depending on when that was printed, depending on who wrote the book. But somewhere between 20 and 25:1, you're typically going to have kind of this medium, very kind of neutral immobilization or mineralization. However, if you get above 25:1, you will start to have a net immobilization. Greater than 25:1, there's just too much carbon there, and the microbes need that in order to decompose or process that carbonaceous material. There's an equation for it that we'll go over. Not necessarily going to go over that yet. I prefer to do that on a board where I can explain what's going on and when. However, if we get below 20:1, we'll have a net mineralization. And so most of our cover crops are going to have a very low carbon to nitrogen ratio, and we will apply that, and we will kind of grow those cover crops so that we can provide a little bit of nitrogen to those microbes so they can begin to decompose or kind of break down some of that crop residue that is left over from a corn, cotton, soybean, or even a hay harvest. So things like hairy vetch, Balanza clover, crimson clover, red clover, any of our clovers are typically going to be grown as a cover crop, and they will provide some nitrogen credit prior to the next season's cash crop. Excuse me, we talked about, if you remember, those clay layers can expand, and that ammonium can then move in between and get trapped in between those two tetrahedral layers. And once those are fixed, it is very difficult for them to come out. I'll explain that in just a moment here. So we have these micas. This might not be the case, but this is just kind of the one that I wanted to bring up because I wanted to kind of show you that while this is not necessarily the type of isomorphic substitution that we were talking about on the previous exam, recall from our lyotropic series that ammonium and potassium are very similar sized. And so we had this, if this was a 2-to-1 clay layer that was kind of expanding, that would expand and we would have ammonium trapped in here rather than the potassium. So you might have it available in the soil, but it is not available to the plant because it is actually trapped in between those. It's kind of locked in those voids made by those tetrahedral layers. And that actually kind of even cements those two together and actually minimizes that shrinking and swelling. So once they're locked in there, it's very difficult for them to be released. Once we have it as ammonium, it can undergo ammonia volatilization. So here we have ammonium, and remember that when we formed ammonium, we took one hydrogen from the soil, which then increased the hydroxyl concentration. Well, this hydroxyl still needs a partner, and it is going to get it from this ammonium that it just formed with. So that hydrogen will dissociate from ammonium onto this hydroxyl and form water, and that ammonia is then given off as a gas. And we're going to talk about this more in depth through urea hydrolysis, because this is probably something that you will encounter when you apply fertilizer. This is a very common in-loss that we're trying to minimize. So we have some of these, if the conditions are right, and let's say you go to apply 100 pounds of nitrogen per acre, and you have, let's say, a high pH, the soil temperatures are high with a low CEC, surface broadcast, and you don't get enough rain to incorporate that into the soil, you can lose like 30% of your nitrogen. So you paid for 100, but you only get 70 pounds of nitrogen in the response from that, because the rest of it was volatilized into the atmosphere. We're going to go over this a lot more in depth when I get back, and y'all have a better understanding of how to combat that. Our final transformation is going to be denitrification. This is going back down from the bottom of our chart where we had nitrate. We must have nitrate in order to have denitrification. And it will undergo these processes where it is then stepwise reduced back to into gas, which is then given off into the atmosphere. All right, so we had this stepwise reduction. There's a lot that goes on in this, and understanding the oxidation states within this. I tend to like to go through this on the board because it takes a minute to get into students' thought processes as to what's happening. But once you understand what's happening through oxidation and reduction, this process seems a little easier. So we have nitrate that is then converted back to nitrite. Then we have these NOx gases, this dinitrous oxide, and then finally this into gas. And so if we get reduced conditions, or if we have a heavy rainfall that fills up the soil profile, we're at saturation, when we have our nitrate in there, we can then begin to undergo this denitrification process carried out by the Pseudomonas and Bacillus species. But if the water drains quickly enough, and let's say you have a sandy soil, that water drains quickly enough, or is evaporated, or there becomes some flush of oxygen in there. And during this process, if these NOx gases get emitted back into the atmosphere, they're 300 times the warming potential of carbon dioxide. And everyone's all up in arms over carbon dioxide with this climate change thing. But we can have a real big problem if we start having these dinitrogen oxide emissions back into the atmosphere. So we need to have low oxygen and a alkaline pH. We need that because the bacteria, the Pseudomonas and the Bacillus do not like low pH conditions. You can still have a lot of nitrogen lost over a field. You can have, and again, you got to remember that it doesn't always stay this way. So how many ever days you might have a flooded field, you could lose up to 1 pound of nitrogen per acre per day. When we're going to see most of those is going to be this after a heavy rain or an irrigation event where our soil profile is saturated, or after snow melt. And then we might have some of these continuous losses over extended periods of time. And then this is just kind of giving you some information about the different types of chemical reactions and how those show you the changes in nitrogen. All right, so I think that's all I got for this video. That's probably a lot to ingest. Just know that we're going to go over it again and again and again until y'all get it. All right? All right.